Okay, good afternoon, everybody. My name is Stephen Rogers from the Energy Conservatory, and I'm going to be talking about understanding the stack effect and building ventilation today. Thanks for participating and for getting registered. We have two other people from the Energy Conservatory with us today. We have Bill Graber, who's in sales and marketing, and we have Colin Olson, who's our staff physicist, and they will be available to help with questions as they come up. And I will go ahead and get started. If you have any questions, we'll try to save those till the end, but I'm going to have Colin and Bill be kind of monitoring the comments and monitoring for people that raise their hands. And if there's questions that are particularly timely, we might interrupt and divert a little bit to answer those questions. Otherwise, we'll go ahead and get started. Yeah, use the Q&A panel to ask questions and raise your hand if you want to talk. We do have, looks like we've got 54 people, so that's gonna be, we can't let everybody talk, but you know, if you have something you want to comment, we'll see if we can get that worked in. Okay, so for those of you who don't know much about the Energy Conservatory was founded in the 1980s, and we are best known for the Minneapolis blower door. That's kind of our primary product that most people are familiar with. Also, the Minneapolis duct blaster is a very popular product that we make. The blower door is used for measuring the air tightness of buildings, and the the duct blasters for measuring air tightness of ductwork. We also make a really innovative product called the TrueFlow Grid. This is used to measure system airflow, air handlers, and furnaces. And we were a pioneer of duct leakage measurement. Before the Minneapolis duct blaster, there was really no practical way to make a measurement of residential duct leakage. And this TrueFlow Grid is a patented air handler flow measurement device. So that's a little bit about the Energy Conservatory. I'll give you a little bit of background about myself. I've been involved with pressure and flow measurement for more than 20 years. I spent 19 years at Emerson. I worked for Dwyer Instruments for a year, and now I've been about 4.5 years at the Energy Conservatory and been president of the company for 2.5 of those years. My education is in mechanical engineering, and I'm fairly new to HVAC, but I've been measuring pressure and flow for a long time and have quite a bit of background. There's a lot of knowledge that I have, and I'm excited to continue to share with the energy, air tightness, and HVAC communities. So I want to start off by introducing a couple applications, and these are some ideas of how you might actually use the stack effect simulator that we're going to show to answer questions that might come up in your work. So the first one is, let's assume you've got a house that's in a hot, humid climate, and the occupants are having trouble with indoor humidity. Their system can maintain temperature, but indoor humidity is not well controlled. So how can you prevent hot, humid air from coming in through the building leaks? And we'll give some examples of different strategies how that can be done, and how particularly the stack effect can play into that solution. We're also going to talk about a large house with multiple HVAC systems. We're going to understand what is the infiltration part of the heating and cooling loads, and where in the house is that load coming in. And then lastly, we're going to look at a situation where a homeowner or customer wants a 500 CFM kitchen exhaust hood, and answer the question, will it depressurize the house, and by how much? What if it's a fairly airtight house at about 1200 CFM 50? Or what if it's a much leakier house at 3800 CFM 50? So think about those applications. Hopefully one of those you can identify with. Maybe that's the kind of a question you've pondered before, or the kind of thing that your work gets into. And so we'll walk through and we'll insert those applications into the training that we go through here today. So first of all, let's define what is the stack effect. The stack effect gets its name from smokestacks. And very simply put, the stack effect is air movement because of buoyancy. And buoyancy happens in air because of a difference in density. And the difference in density happens because there's a difference in temperature. So, and also, if you have two masses of air, that are separated by a building, for example, that difference in density creates a difference in pressure. And that's what we'll be looking at today in the simulator is the pressure and the airflow that gets driven through the building leaks. That difference in pressure is what drives leaks through a building. So the diagram at left is just showing an example of a smokestack. And obviously in a smokestack, the air or gases inside the stack are warmer than outside. And because of that density difference, the warmer, less dense air tends to be buoyant in a mass of colder, denser air around it. And so air is drawn in this location at the bottom of the stack and comes out at the top of the stack. So that's basic definition of what the stack effect is. Okay, so we're going to be using this training simulator called CStack, and this program was written by Dr. Colin Olson back in 2003. And Colin wrote this for a presentation that he gave at one of the building science conferences that that the Energy Conservatory attends, just for the purposes of a single seminar that he did. And it has stuck around and been very useful to us ever since. It's a very excellent way to understand the relationships between air tightness, stack effect, outdoor temperature, and ventilation, because they all interact inside the building. And if you want to download this, you go to energyconservatory.com, look under products and software, and then you'll see the CStack training simulator. And you do need to give us an email and register, but there's no charge for it. And then you can download the software, you can run it and do whatever simulations are useful in whatever you're working on. Okay, so I have also put together this cheat sheet. This is written quite a while ago, and it uses sort of old school keystrokes to control the program. And so I find it helpful if you print up something like this and just put it next to your keyboard, so that as you're running simulations, you can remember what the keystrokes are. After you've done it for a while, you'll remember what they are, but at first this is quite helpful. So if you want to take a screen capture at this moment, then you can print that screen capture up, or if you simply email one of us, we can send you a copy of the cheat sheet and make it easier for you to learn the program. So like I said, a little bit old school, but still very useful. And every time I show it to people, they're amazed at how useful it is in helping to actually understand what's going on inside of a building. So with that, I'm gonna pull the app over here and we will start doing some simulations. So this is what the program looks like. And you can see that when you pull it up, the default conditions are as shown here. Defaults to a 2-story house that has an air tightness measured of 2000 CFM 50. And if you're not familiar with air tightness measurements, the air tightness measurement is made with a blower door like the Minneapolis blower door that we sell. And that's really the most practical way to actually find out how tight or leaky a house is. So here you have the air tightness, and that can be controlled. We'll walk through that. But before I change the air tightness, I want to show the other controls here. Below the house here, you have a slider for the outdoor temp. And as you can see that as I move it to the left, which makes it colder outdoors, you can see that the pressure is going up at the top and getting lower or more negative at the bottom. And that the amount of airflow, which is shown in green there, gets larger and larger. And that's because the greater the temperature difference between indoors and out, the more stack pressure, and the greater stack pressure drives more airflow through the leaks. So that's the basics um, of the outdoor temp. So in green, you can see shown how many CFM of air are flowing out and how many CFM are flowing in. And to begin with, in equals out from the natural infiltration, but those will change as we start using forced ventilation with a fan. So a couple things to point out: 2,000 CFM 50 is how leaky the house is, but it's not leaking 2,000 CFM, and that's because the pressure's not at 50. The pressure here is at minus 1.5 pascals at the bottom and plus 1.5 at the top. So the leakage that occurs at this pressure is much less than what gets measured at 50 pascals with a blower door. Okay. So next, I want to show you what happens when we start changing the air tightness of the house. And the easiest way to do this is to use the keys T for tight, M for medium, or L for leaky. And of course, it starts with medium. But let me move it to just by press the T for tight key, and I'm going to leave everything else the way it is. And so now we've got a house that measures 1,000 CFM 50. And notice now our natural infiltration is down to 42 CFM. I'll go back to medium and just toggle back and forth here. You can see we were at 85 CFM when the outside temperature is 42. And now if I make it a tight building, this 85 CFM goes down to 42. But also notice that the pressures haven't changed. The pressures are related only to the difference between indoor and outdoor temperatures and to how tall the building is. And we'll change the height of the building in just a minute and see that. But the pressures don't change, only the flows change, because when you have a leakier house, the same pressure will push more airflow through the leaks. Okay. Another thing to notice is that in these conditions here, if I have a house that measures 1,000 CFM 50, which is tight, and then I go to medium, which is twice that much, the natural infiltration is going to be approximately proportional. So if I double the CFM 50 measurement, I've gone from 42 to 85, approximately twice as much leakage. And so the natural infiltration at certain conditions will be proportional or roughly proportional to the CFM 50 that you measure. Okay, so that's how you control indoor and outdoor temperature, and the air tightness of the house. Let me also show you that when it's cold outside, the air inside the house is less dense, it's buoyant, it wants to float up. And that causes a positive pressure at the top of the house. So the house tends to leak out at the top and leak in at the bottom. So it's almost like it's sucking in at the bottom and blowing out at the top because of the buoyancy. But if I change the outdoor temperature and make it warmer outside, I've made it 97 degrees outside. Now you can see that the opposite is true, that in the summertime when it's cooler inside and hotter outside, now you're sucking the air in toward the top of the house and it's going out at the bottom. So sometimes this is called the reverse stack effect, if you think of the stack effect being what happens to a warm mass of air wanting to go up. It's still the same effect, but some people call it the reverse stack effect just to denote that the air inside the enclosure wants to go down rather than up. Okay. So now I want to show you can change the number of stories, and I'm going to restore the default conditions here. We're back to our default conditions of 48 outdoor temperature, 71 CFM of natural leakage, and 1.2 pascals. Notice what happens. I'm going to press number 1, which is going to change this from a 2-story house to a 1-story house, which is about half as high. And you'll notice that the pressures are now approximately half what they were. The leakage is lower, but it's not half because it's not, the leakage isn't proportional to the pressure. There's a more complicated relationship there. So the leakage gets lower, the pressure gets lower in a shorter house. Now if I go from the 1-story house back to the 2-story house, again, I'm up to 1.2 and 71. And now if I increase that to a 3-story house, you'll see that now my pressure goes up to 1.7, and now my leakage goes up to 92 CFM. So the leakage that occurs in a house, it depends not just on the CFM 50 measurement, but also how tall it is. So remember, all 3 of these houses were houses that measured 2000 CFM 50, but a 1, 2, and 3-story house will all leak different amounts just because of the difference in height. Okay. So now I'm going to jump to one of those applications that we looked at in the beginning. And that was, let's say we've got a large house that's a 2-story house and has multiple systems. And let's say that it was a large house, but was not built with particularly airtight construction. And so it measures in at 5,000 CFM 50. So I'm going to increase this value here, the air leakage measurement, to 5,000. And now, and I'm going to make it a 2-story house. And you can see that under these outdoor conditions, we have 177 CFM leaking in and 177 leaking out. But in this case, the question is, where's the air coming in and how much heating and cooling load is that causing for us? So those of you that are in the HVAC industry know that the way that sizing is done for a house is by looking at, when you size the heating and cooling equipment for a house, the way that that's done is by looking at what happens to the house, what are the loads at design conditions. So let's take this 2-story house and let's say that it's in a climate where the cold design temperature is 30 degrees outdoors. And you'll see that what happens here is at 30 degrees outdoor temperature, we've got more leakage because, of course, I made it colder. And we've got a leakage of 275 CFM. And that's useful to know, but it doesn't really help you with loads. And so I want to refer you to another tool called RedCalc. Some of you are maybe familiar with this. And RedCalc is a tool, I'll show you, I think I'm just going to jump ahead in the, in the slides here. So if you go to redcalc.com/design-infiltration, you'll find this calculator here. And what I did here is I put in these numbers. You put in the CFM 50 measurement at 50 pascals. And most of the other things, if you don't know them, you can leave them as default. But if you have better information about, for example, the pressure exponent can be known by doing a multi-point blower door test. Shelter and terrain classifications, you'd have to look up those references. If you've done thermography, you might know something about whether more leakage looks like it's coming near the ceiling or the floor or the walls. And then here's where you put in your design conditions. You can see that on this screenshot that I took from RedCalc, this is that house in summer conditions. So we're trying to keep the indoor temperature at 75 and the outdoor design temperature, or the hot day that you're designing for, is 97 in whatever climate this is. And then you also need to know a design wind speed, and that I believe is available in the ACA manuals if you're doing sizing according to the ACA. So what this is telling us is that the stack effect is inducing about 183 CFM of leakage. The wind is inducing 140 CFM, And then you combine those two in a, well, it's a statistical combination that's done to get 230 CFM. That's how much leakage happens under those design conditions. And that corresponds to a heat gain for your cooling calculations of 5,400 BTUs per hour. So make a note of that 5,400 BTUs per hour in your mind, and we'll go back here. Let me get back to the app here. And that was at an outdoor condition of 97 CFM. Okay, there's a difference here between what the other calculator shows because this assumes an inside temperature of 68, which is cooler. So you'd actually maybe want to reduce this a little bit to get the same difference in temperature, and that would give you about the same number that's shown in red calc. But the important thing to recognize, we've switched from heating to cooling here. But in a cooling situation, most of your infiltration is coming into the house on the upper floors. And you're leaking conditioned air out in the lower part of the house. So that can tell you some information that's useful for planning the HVAC system, especially in a house that's large and leaky. As you start looking at humidity and how to control humidity, the humidity is all coming in the upper part of the house here. You probably don't have nearly as much of a humidity load. You don't need to do as much dehumidification in the lower part of the house because the air that comes into the lower part is coming from upstairs. It's already been conditioned. But that upper system, let's say, like I said, this is a house with multiple systems. Let's assume they have an upstairs system and a downstairs system. That upstairs system is going to be working harder because of this warm air coming into the house. And the downstairs system kind of gets a pass because the air that's entering the basement, or not the basement, but the lower floor, has already been conditioned from upstairs, and then you leak some conditioned air out. So that means that design load, at least on a day when there's no wind, is mostly going to affect the upstairs system. But we'll talk later about the effect of wind. You can't assume this is the case always, because on a windy day, you actually don't have pressure high and low. You actually have it more side to side on a windy day. Okay, so that's a brief look at number of stories and how you can relate the leakage to the design loads. Yeah, our tool doesn't do everything, but you can look at this information, see the leakage, and then you can look at where is it coming in and how many BTUs is that by using the RedCalc tool. Okay, so the next thing I want to talk about is leakage distribution. I mentioned that you might know if the leakage is more toward the upper or the lower part of the house, and if you do, you can press the V keystroke here, and that will change your leakage from being evenly distributed high and low to saying that it's now biased more toward the ceiling. And you'll see that this neutral level has changed. We haven't talked about that yet, but the neutral level is where the pressure in the house is changing from being negative to being positive. And that's the level in the house where there's zero pressure difference between indoors and out. What that means is that any leaks that fall right on this neutral level, even if they're big holes in the structure, they actually won't leak as long as the neutral level remains at that level. Most of your leakage tends to happen at the higher and lower points in the house where the pressure is greater. And so if you press the V again, you can push the leakage toward the floor. So maybe you know that this is a house that's got a crawl space, and maybe the floor is not well sealed at all, and so you've got a lot of leakage between the through the flooring and the subfloor. This might be a way to model that house if you know that the floor is much leakier than the ceiling, for example. Okay, and again, thermography, if you've got a thermal camera, that's a way that you can get some idea of where your leaks are coming from. Okay, so I'm going to restore the default conditions here. Um, and now we're going to talk a little bit about ventilation. So far we've just shown that what happens with air tightness, the height of the building, and the outdoor temperature. But now we're going to add ventilation. So the first thing I want to do is start with balanced ventilation because it's easier. And to do that, you press the E button and it'll change from being a fan to being an ERV or an HRV. An ERV or HRV, if you don't know what that is, that's an energy recovery ventilator or a heat recovery ventilator. And both of these devices have two streams of air, one flowing in and the other flowing out, which are balanced. They're intended to be the same number of CFM flowing in and flowing out. And that makes things easy because it doesn't really change the natural infiltration. So if we have an ERV and let's say that it's going 50 CFM would be a common setting for an ERV or an HRV. And you can see that, we had 71 CFM naturally coming in and out because of the building's leakage. And we have now added 50 CFM more, giving us a total of 121 CFM of ventilation at these conditions. Of course, if we change the outdoor temperature, and make it on a very mild day that's only, very close to the indoor temperature and outdoor temperature are nearly the same, now you've got less total ventilation, but you still have the same 50 CFM from the ERV. Okay, so ERVs and HRVs are pretty easy to simulate. They don't disrupt the natural ventilation. But now I want to show you what happens when you add ventilation with an exhaust fan. If I press the F keystroke, it changes it from an ERV back to a fan. And now let's say that instead of a balanced flow of 50 CFM, we've got 50 CFM of exhaust flow. So let me show you what's happening here. I'm going to back the exhaust flow back down to 0. And now you can see that we've got 98 CFM coming in and 98 going out toward the top. But as I add an exhaust fan that's blowing air out of the house, it's actually making the neutral level rise. And watch what's happening to the in and out flow numbers. So by the time I get to 50 CFM, I now have 124 CFM coming in. My neutral pressure plane has gone up, and I've got 74 CFM going out through the leaks, plus another 50 CFM going out through the exhaust fan. Remember that because the building is not going to implode or explode, the flow into the house has to equal the flow out of the house. So if you've got 50 CFM going out the exhaust and 74 going out through the leaks, then you must have 124 CFM coming in. So what's happening here is the exhaust fan is changing the balance of the natural infiltration. It's raising the neutral pressure plane. And because it disrupts the natural infiltration, what that means is when you exhaust 50 CFM out of a house, you have really only added about 26 CFM of natural or of additional forced ventilation. The natural infiltration without the fan was 98. We've added only about 26 because of this change in the natural infiltration. Okay, so let's take a look at the effect of air tightness now in this situation where we've got 50 CFM of exhaust. So I'm going to change this from a medium house at 2000 CFM to a tight house by pushing the T button, and watch what happens here. So now the neutral pressure plane has gone even farther up. The natural infiltration has gone down, of course, because this is a tighter house. And we still have our same 50 CFM of exhaust, but we've only added 27, just slightly more than half of the of what's going out the exhaust fan. Okay, so there are frequently debates among people about whether it's better to have supply-only ventilation or exhaust-only ventilation. And the answer to that question really does depend on your climate. But sometimes I think there's a misperception that if I have exhaust ventilation, it's going to depressurize the entire house and I will have air flowing in at all the leaks. And that's really not true unless a house is really tight. With a flow of just 50 CFM, which is a typical design for exhaust-only ventilation, a medium house at 2,000 CFM, I've really only moved that neutral pressure plane up by maybe 3 feet. So in the same house, if I had no ventilation, it would be balanced, 98 CFM in, 98 CFM out, and the neutral pressure plane, we assume is halfway between the ceiling and the bottom of the foundation floor. But when I increase the ventilation to 50 CFM, notice that I'm really not raising the neutral pressure plane very much, unless the house is really tight. So a house that's 1,000 CFM 50, or let's decrease that further, and let's say that we've got a house that's like 500 CFM 50, really tight house. Now you see, if you have a very tight house, a 50 CFM exhaust fan might indeed depressurize the entire house, but only if it's a really tight house. There are not that many houses that are less than 500 CFM 50. Okay. Now, I want to jump into that first application, which is talking about humidity control. So we're going to change this back to a one-story house. We're going to take our ventilation back to 0 here, and okay, and now we're going to look at summertime conditions. So we're going to make it 95 degrees outside. And you can see that I'm going to make this a one-story house. So again, this is a house where we assumed that the occupants are having trouble with humidity. The system will say is able to maintain the set point, but it's not able to control the humidity. And so the question was, how can I prevent that hot, humid air from coming in? You can see that even, these conditions here, we've got about 50 CFM and it's all coming in the higher levels of the house. So what can you do to improve that? Well, in hot, humid climates, it's probably, there's a good reason to say that supply-only ventilation is a better way to do things. So let's say that you're able to do some air sealing on this house, and you're able to air seal it and get it from 2,000 CFM down to 1,000. Let's see, oops. Yeah, 1,000 CFM 50. So you can see that you've reduced quite a bit of the infiltration load. Again, I'll make this back to medium. We were at 52 CFM, and now by making it tight, we're down to 26. But I can also add supply-only ventilation. And when I say supply-only ventilation, this is often a fan that is drawing air from outdoors and drawing it into the return duct of the air conditioning system. And let's say that we're drawing in 50 CFM. So look what's happened here to the neutral pressure plane. It's moved almost to the ceiling. And so now we've only got 3 CFM of air coming in naturally. So you've almost completely eliminated the air that's leaking in. And by directing the air that comes in, the supply ventilation air normally would go, or could go through the air conditioner. So now you're taking this outdoor air, 50 CFM of supply, and by routing it through the air conditioner, now almost all the air that's coming into the house is going through the air conditioner and being conditioned, and most of your leakage is leaking outward. So that's probably good for building materials to keep them dry, and it also dramatically reduces the humidity infiltration load. If you look carefully at load calculations that are done, the infiltration is normally a very large part of the latent load, which is the amount of humidity that's coming into the house or generated in the house. The humidity that has to be removed, some of it comes from people breathing, cooking, taking showers, and things like that. But unless a house is fairly tight, a large portion of the humidity that you have to deal with is just leaking in from outside. So if you are able to use supply-only ventilation and improve the air tightness of the house, you have a much better chance of controlling the humidity because you're actually reducing significantly the amount of humidity that you have to deal with. All that would be left is the humidity that's generated inside the house by the occupants. Like I said, bathing, breathing, and cooking all generate humidity. But that's normally a lot less than what's coming in. No, not a lot less. It depends on the number of occupants. But you can reduce it a lot by controlling the infiltration of the house. So in a retrofit situation, though, it might be fairly difficult to decrease the infiltration from 2,000 CFM down to 1,000. But let's say that you started with a leaky house at 3,000 CFM, and before we had the supply ventilation, let's say that you were at, so you got one-story house, 3,000 CFM 50 is what it measures, and you got 78 CFM coming in those upper levels. Now you might not be able to get to 1,000 CFM 50, but what if you can only get to 1,500? You might be able to do that with a good retrofit air sealing. And then I keep my same 50 CFM of supply ventilation. And if I can achieve that, now instead of having 78 CFM coming in, I've got only 16. So even if you don't get great air tightness, you can dramatically decrease the amount of humid air that's coming into the building, and that helps with comfort. Now, of course, there's a couple caveats here. If you're doing some air sealing, you're going to reduce the load, and that might mean that you need a smaller system in order to get enough run time to have adequate dehumidification by the system. But that's, we can't cover everything in this seminar. Okay, so moving on here, I'm going to restore the default conditions again here. And I want to now look at this last application, which is depressurizing the house with an exhaust hood. So there's another keystroke here, which is B for big or S for small. And if you press the B button for big, you can see that the instead of your fan going from minus 100 to plus 100 CFM, now it goes from minus 1,000 to plus 1,000. So what you have here is a good way to simulate a lot bigger ventilation flows. So let's take a look at the exhaust ventilation, and let's answer that question. And the question went like this. So if I've got a house that is 1,200 CFM, so I'm going to go to tight here, and then I can press the plus button to increase this up to 1,200 CFM 50. And now let's say I've been asked to install this exhaust hood in the kitchen that pushes 500 CFM. And you can see what's happening here. At 500 CFM in a house that's tight, like 1,200 CFM 50, I could easily be depressurizing the house by 10 to 15 pascals. So we showed that with a 50 CFM exhaust from a bathroom fan or for ventilation, it doesn't affect the depressurization of the house nearly as much. But now we put in a large fan like a kitchen range hood that's pushing tons of air, and now you potentially have a big problem. At depressurizations like this, you can start having trouble opening doors. It can be difficult to open doors. If you do have natural combustion appliances in a house like this, if you depressurize a house by this much, you're almost sure to backdraft appliances. Um, and that's a safety concern, with carbon monoxide. But let's take the same situation, the same 500 CFM kitchen exhaust hood, and let's put it in a leaky house. So I'm going to change and press L to make it leaky, and then I'm going to go even leakier still and go up to 3,800 CFM, which is not out of the question. And you can see now that my pressures are not nearly as large. I've got about -1 Pascal at the top and -3 at the bottom. So in a leaky house, an exhaust hood that pushes that much air is much more, much less of a concern for depressurizing the house. It still could be a problem with natural draft appliances, but it's less likely to be one and to be a problem. And the thing to do is to do some measurements and some simulations. We do have tools that help with simulations for combustion appliance zone safety as well. That's not really the focus of this webinar, but please contact us if you have questions about that as well. Okay, so that's a summary of what happens with kitchen exhaust hoods, and being careful to understand the depressurization before you go adding an exhaust hood with no makeup air. When you get into these really high volume exhaust hoods, which I think are becoming more and more popular, you have to be much more concerned about the need for makeup air. Okay. So let's move forward here. We talked about calculating infiltration loads, and I want to explain stack effect and wind effect together. So the C-Stack tool does not simulate wind, but I did just a graphical simulation to shows what happened when there is wind. So what I've done here is I've simulated a wind that looks like this produces about 2 pascals of wind pressure. So that's maybe 4 mile an hour wind, which is not, 4 miles an hour is not a high wind by any means. But when you do that, what happens is you'll see this neutral pressure plane is no longer level. The neutral plane goes up on the windward side and down on the leeward side. So there's still a stack effect, and you'll still have, a lower pressure at the bottom of the house, higher pressure at the top, but you sort of get a mirror image left and right, or windward and leeward, in addition to having higher and low pressure above and below the neutral pressure plane. So you can see that in the top corner on the windward side, you've got plus 0.7 pascals, and on the leeward side, at the bottom, you have minus 0.7. Then you've got minus 2.7 and plus 2.7 in the opposite corners of the house. So when you combine stack and wind together, you actually start to tilt that neutral pressure plane, and you can see, I've got wind speed at the bottom here versus the pressure that is created by that wind speed. And you can see that even if you get up to 10 miles an hour, you're creating a wind pressure something like 12 pascals. And 12 pascals is more than you're usually going to see from stack effect unless it's a really tall building. So that means by the time you get up to about 10 miles an hour, wind is dominating the situation, and it's not the stack alone anymore. You'll still have a stack effect, but in this case, the wind starts to become greater, somewhere around 5 to 10 miles an hour. Okay, So that's the effect of stack and wind together. As I said, the tool doesn't simulate that, but this is what it does if you want to try and understand that. Okay, so let's summarize the applications that we threw out to begin with. We looked at a hot, humid climate, and in the hot, humid climate where we're having difficulty controlling the humidity, the summary of that application is if you can do retrofit air sealing, and if you can do supply only ventilation into a return duct, then almost all the incoming air is going to go through the air conditioner, and you're going to have a much easier time controlling humidity. As I mentioned, you do need to be concerned about sizing your equipment, because if you tighten up the house, especially if you're going to add insulation, you might have a much smaller load and need to downsize the equipment, because it's it's well known that if your equipment doesn't run long enough, you have difficulty with humidity control. So you want to make sure that you've adequately sized the equipment for the new load of the house, especially since you're probably reducing the load if you take some of these measures. In this large house with multiple HVAC systems, we said this is a large house at 5,000 CFM 50. And what we looked at there was if your heating design temperature is 30 degrees Fahrenheit, and that house with 2-story, you're going to have about 280 CFM coming in, and that correlates to about 12,900 BTUs per hour. So if you're doing heat pumps, that's like a ton of 1 ton of heating you have to add, just because of the design infiltration load, and it's coming in at the bottom of the house. That's where you're going to see that load. The opposite is true in cooling. 2-story house, if you've got systems high and for upper floor and lower floor, you've got 180 CFM, so less airflow coming in. But here you've still got about a half a ton of cooling that's happening, or that needs to happen because of the infiltration, and that's coming in at the top of the house. Remember, like I said, you probably don't want to allocate all of this load to the top floors, because on windy days, that's not going to be the case. On windy days, it's going to be coming in the windward side of the house and leaking out on the leeward side of the house. But it gives you some idea what you're dealing with. And then to summarize the 500 CFM exhaust hood, so a 1200 CFM 50 house, you'd be depressurizing a lot, minus 11 to minus 15 pascals, something in that neighborhood. But a leaky house at 3800 CFM 50, you'll be depressurizing by a lot less, and maybe you wouldn't need makeup air in that situation. Okay, so I wanted to wrap up here with just sort of a couple of interesting activities. If you want to do some testing to learn about the stack effect, there's some things that you can do with just a good micromanometer and data logging tool. You can watch this happen. And I gave this webinar at the end of March when we were just starting into our COVID pandemic, and I was feeling a little bit of stuck at home. What should I do that's interesting? And so there are a couple things I did that you can do just to learn about the stack effect. So here you can just put a piece of tubing in the freezer, let it get cold for half an hour or something, and then remove the tubing and connect it to the micromanometer. So this was a piece of tubing, and then you want to throw the tubing down the stairs, or make sure it gets some vertical distance on it. This one went through a couple floors, or went from the upstairs downstairs through to the downstairs in my house, and you can see that we had about 3.8 pascals of stack effect, because the air inside the tubing was cold and the air outside the tubing was not. So you've got this denser mass of air inside the tube, and it's sucking on the pressure port of the manometer, and so you can see it creates a negative pressure. But interesting to note is that it takes 10 to 15 minutes for that air to warm up, and it's not going to warm up and it warms up, there's not any flow happening in that tube because you've got only one end of the tube is open. The other end of the tube is connected to the manometer. There's no airflow through that. So this is just the air around the tube warming through the tube wall and then warming the air inside the tube, and that takes a while. So this is something that's important to know if you test large buildings or tall buildings. You want to keep your tube fairly level if you can. Don't throw it down a big hill or out an upper story window. Normally this isn't a big deal because you throw a tube out the door and it's at approximately the same level. So there's not going to be much stack effect there. But if you are in cases where you're throwing tubing down the side of a building and there's a lot of vertical there, and the tube is warm and you throw it outside where it's cold, you get the opposite effect. So this is just something that you can try if you're interested. Another thing that I did is I looked at measuring where is the neutral pressure plane in my house. And I did that. This is by putting one tube on one channel of the manometer out the top of a high window, and on the other channel I put a tube out the bottom of a low window. I also want to point out this basement door here because we'll see what happens when I opened this basement door, because it moved the neutral pressure plane by creating a huge leak down low. So you put the tubing out the window. You want to try and get the window closed as tightly as possible, but you can't kink the tubing. So if you have smaller tubing, you can use that to get the window nearly shut. And in the case that I measured this, the outdoor temperature was 37 degrees. And so this is what I measured. This was a nice calm day. If it's not a calm day, you'll have a really difficult time doing this because the wind is going to be bigger than the pressures that you're measuring. But what you can see here is out of the upper window at the top there, I measured plus about 1/4 of a Pascal. And in the lower window, I measured minus about 2.5 pascals. What that tells me is that my neutral pressure plane, where I would measure 0, is much closer to the upper window than it is to the lower window. It's slightly below that upper window. And now I mentioned that basement door. And what you can see here is when I opened that basement door, the pressures both went up, so that the difference between these two is still about the same. The stack effect is the same, but by opening that door, the neutral pressure plane moved way lower, or another way to say that is the lower window was much closer to 0 and the upper window was much farther from 0 when I opened that door. Okay, so comparing what C-Stack tells me to what I measured. So C-Stack tells me, I put an outdoor temperature of 34 here because I actually keep my house warmer than 68. I keep my house about 72. But you need to make sure that the difference in temperature is the same. And C-Stack says that I would have 4 pascals of stack effect under those conditions, but that would be measured from the bottom of the lowest floor to the top of the upper floor ceiling, which is about 17 feet. But the vertical difference between my pressure taps was only about 11.5 feet, and I measured 2.7 pascals. So if I take that 2.7 pascals and I multiply it by 17 feet divided by 11.5 feet, I indeed get 4 pascals, just like C-Stack says. The interesting thing to look at is, where does that tell me my neutral pressure plane is in my house? So that tells me that my neutral pressure plane is about 18 inches below this point. And if the neutral pressure plane is by definition where half the leaks are above and half the leaks are below the neutral pressure plane, then where are all my leaks? Most of my leaks are in my ceiling. That's what that tells me. Okay, so that's all I've got for you today. We've got some time for questions. So Colin or Bill, if you want to mention any questions. I haven't been following the chat, so I don't know if we've had questions come in, but please raise your hand or go ahead, Bill.
I was just going to say, yeah, you've got one from Nick that maybe between you and Colin you can answer. It was when you were talking about the ERV, HRV. And while you guys read that question, I'll answer the other one out there, which is, should we be concerned about running a blower door test because of COVID, which is a common question right now. And so, we are certainly not the right people to answer that definitively. That's a health related question. But we have been compiling just some thoughts between Steve and Colin and Gary Nelson and Paul Morin on what are some thoughts about what might make it safer or less safe when you're doing a test. And again, it's not the answer, but you'll find that if you haven't signed up for our newsletter, that will be in our newsletter coming out next week, and it will be posted to our website. So we do weigh in on that and have some thoughts related. So I don't know if I gave you guys enough time to read that question and decide how you want to answer Nick's question.
Yeah, Colin, did you read that question? I think I know the answer, but I'd rather you took a swing at it. Did you read Nick's question?
Yeah, sure. Yeah, it's a good question. Does it matter vertically within the house where the ERV or HRV is located? And for the most part, I think the answer with regard to the stack effect is no. The effective pressure on the building itself is almost none whatsoever, as Steve showed, regardless of where vertically that is installed. There could be a very slight difference because, as Steve showed, there are pressures in those walls that are different at the bottom than at the top. So if that system has what would be called a weak fan curve, or it doesn't always give the rated flow when there are changes in pressure, you could have some very slight changes due to the vertical location. But I think that's a secondary effect and almost not worth considering. Steve, anything you want to add?
Well, yeah. So the thing to consider is what you have to ask is what is okay. So you're sort of answering the second half of the question. If you balance your house on a certain day, will it be in balance on all other days? Actually, the answer is if the fan curves are parallel of your fan that's pushing the air in and pushing the air out, and if they are entering and exiting at the same level, then it won't matter if they're high or low. But if you are sucking air in at the top and down at the bottom, and you have weak fan curves such that 2 pascals of stack effect is actually going to get you to a significantly different flow on your fan curve, then yes, it will have a small effect. Okay, other questions? Anybody want to raise their hand and ask a question live? We can do that too.
Well, while we're waiting, Steve, to see, we're basically out of time. It just turned the hour. Just to let everyone know that we will be posting this in about a week's time on our website. There'll be a link to our YouTube channel where you can find this.
Okay. Bill, did you get somebody put their BPI number in the chat?
Yep.
Did you get that?
Got that noted.
Down?
We'll make sure that gets added before we submit this. Yep.
Yeah. Okay. All right. Well, thanks everybody very much for coming. We appreciate your time and hope that you learned something. Feel free to download the app from our website and put it to good use. It's been useful in helping us to understand how all these things interact. It's more complicated than most people think. So let us know if you have questions that come up later on. And thanks very much.